In this video, we're going to take a look at bonding that happens within metals, both metals of the same atoms and metals of different atoms. So metals like to come together in what we call metallic bonds. When metals come together, since there isn't a nonmetal to take on those electrons and make an anion, they just kind of let their electrons flow freely throughout that entire sample of that metal, and they're able to drift and move throughout that entire sample because not any of those atoms of the metals want those electrons. They can move from one side to another all around and about as that metal is changed and manipulated. They are held together, though, just kind of like ionic compounds, because you do have positive and negative still. Those metal cations, because they release their freely now flowing valence electrons, and the positively charged cations are left behind, and you still have positives and positive negatives like that of ionic compounds. Because of these freely flowing electrons, we see some interesting properties that metals possess that we didn't see with ionic compounds. First of which being the fact that they are conductive. Ionic compounds, when you melted them down or you dissolved them into water and made a solution, they could conduct electrical current, but metals can conduct electrical current in their solid state. Because those electrons are freely flowing around, electricity is the free flow of electrons and the movement of electrons, and you have able to make a closed circuit passing those electrons along. So when an electron is put into one side of a sample of metal, it is able to kind of push along like dominoes and kick another electron back out the other side. No metal cation wants to take back on the electrons that they already released, so that extra electron is then sent back out on its way. Also, the fact that they're ductile and malleable has to do with these ability of freely flowing electrons. Ionic compounds are very rigid and they break and shear very easily because as you try to manipulate their shape, you end up moving the like charges next to each other. And you're breaking apart the opposite charges that were keeping them held into place, now putting them next to each other, causing them to repel, which is why it breaks into little pieces. But with metals, since those electrons are freely flowing, they kind of act like a lubricant between the cations of the metals that are there, and you don't have that like charges next to each other. Electrons move as you change the shape of that metal, and you don't have cations next to each other. Again, those electrons stay in between, positive, negative, keeping them together in one piece. But like that of ionic compounds, metals do make crystalline structures. Every single metal makes their own crystalline structure, which is a repeating, three-dimensional, orderly, compact crystal structure like we saw in ionic compounds. Some metals can make multiple different ones based upon their temperature and how they are formed together, but most have just one structure, which we know already. Each one of those different structures contains 8 or 12 other cations that surround that cation of that metal in that crystalline structure. Here are the 3 different crystalline structures which we see happening with metals. You see body-centered cubic, like the chromium on the left, face-centered cubic, gold in the center, and hexagonal close packed like the zinc on the right. The body-centered cubic, we see 8 different cations, again surrounding that centered, body-centered cation in the middle, the 4 in the square up top, and the 4 in the square down below, giving you 8 other cations. Gold in the face-centered cubic has 12 other cations, and hexagonal close packed like we see in zinc also has 12 other cations that surround every particular metal cation in that crystalline structure. Oftentimes we see metals in what we call an alloy. Alloys are a mixture of a metal with other atoms of different elements, oftentimes other metals, but it could also be a metalloid or a nonmetal. We do this because metals on their own possess properties which we would like and use, but by adding in these other elements, it gives them even better properties that we can add into it. We see this with gold. Oftentimes jewelry that's made out of gold isn't 24 karat gold, pure gold, because gold is very malleable, very soft. They add in copper to make it stronger, and therefore most jewelry you find in 14 karat gold or 10 karat gold, again indicating how much gold is present in that alloy. Another familiar place to see this is in steel. Steel is iron. We use it to build large structures that we want very strong, and iron by itself is strong, but we can make it even stronger by adding in carbon to it. So carbon with the steel makes it a stronger metal, allowing it to sustain more weight, make it more rigid, and have the ability to keep its structure. So that steel is what we call an interstitial alloy. It's an alloy in which you have larger atoms then combining with smaller atoms of a different element that fill in the little holes between them. So iron that has an atomic number of 26 and it has 4 rings worth of electrons and it's a much larger atom than carbon, those little carbon atoms can fit in between the iron atoms in its crystalline structure. It's like taking a bucket full of softballs and then adding in golf balls to fill in those little holes between, making a much more complete, filled out structure. Gives it more strength, again making it more rigid, allowing it to sustain even more force. The other type we see is a substitutional alloy. We just discussed that with gold. Adding it with copper, they do make the same type structure, same crystalline structure, so they do work well together, and those copper are replaced in the gold. We also see that in bronze. Copper with tin. Tin and copper also make the same crystalline type structure, so those tin cations can replace the copper cations within a structure, adding it together, again giving it better properties than the copper on its own.